Now in this video lecture we will go through another topic, crystal lattice and unit cell, right? When we say crystal lattice, what is the meaning of lattice? Once you know the meaning of lattice, you will little bit get an idea what we are going to study, right? Crystal lattice, right? Lattice is an English word which is related to some kind of structure, right? So this will represent some kind of structure. So crystal lattice, crystal structure, right? So this crystal lattice will going to tell us about the structure of crystal. When we talk about structure of crystal, we have already discussed in previous video lectures that crystalline solids are true solids, right? Crystalline solids are true solids and amorphous solids are pseudo solids, right? And we said that crystalline solids are rigid, right? They are rigid, they are incompressible, they have mechanical strength. Why? Because of the arrangement of particles, right? How particles are arranged in the crystal structure and how they are packed, right? That defines the rigidity and incompressibility of crystals, right? So this crystal lattice is also known as space lattice, right? Crystal lattice or crystal structure, right? So now if we know that in crystalline solids have geometric forms, they have geometrical shapes, right? Why? Because the constituent particles that make up a crystal are arranged in a definite geometrical fashion, right? So we write here that constituent particles, and these constituent particles may be atoms, ions or molecules, right? Constituent particles are arranged in a definite geometrical fashion, definite geometrical fashion, right? In 3 dimensions, right? Within the crystal, within the structure of crystal. Within the structure of crystal, right? So these particles, how they are arranged in the crystal, right? These particles, since they are arranged in a definite geometrical fashion, right? This arrangement of particles give crystals definite shape, right, or geometrical forms, right? Now this we have already understood in our previous video lecture. Now these constituent particles, right, that gives definite geometrical forms to the crystal, right? If somehow using some experimental techniques like diffraction techniques, we get to see how these particles are arranged in the crystal, right? Suppose we have a crystal, say all the particles are arranged in this way in the crystal, right? If this is the way particles are arranged in the crystal, right? So this is its geometrical form, right? Say particles are arranged here at these corners, right? Now crystal lattice. So we may also say that these constituent particles, right, in crystal structure are arranged in a regular array, right? It's kind of a regular arrangement of particles, right, in 3 dimensions. Since crystals are 3 dimensions, so these particles within crystal are arranged in 3 dimensions, right? So what this space lattice or crystal lattice tells you, space lattice or crystal lattice will tell you how these particles are arranged within the crystal, right? If using some experimental techniques like diffraction technique, you find how these particles are arranged in the crystal, right? Once you know the position of particles, right, and if you draw the position of these particles, right, using points, right, in 3 dimensions, right, you will know how the crystal looks like. You will get to know how the structure of crystal looks like, right? So this arrangement of points, right, in space, that represents the position of atoms, ions, or molecules in the structure of crystal, right, is known as space lattice, right? I'll repeat again. Space lattice will simply, in simple words, space lattice tells you how the atoms, ions, or molecules are arranged within the structure of crystal, right? If you draw the position of these atoms, ions, or molecules in 3 dimensions, right? In 3 dimensions, what you get is a crystal lattice. So crystal lattice in a way shows how particles are arranged, right, in 3 dimensional crystal systems, right? So just let's try to understand it in 2 dimensions, right, just to make it little simpler. Okay, one example. If we talk about arrangement of points, here I said if you arrange points in 3 dimensions based on the location of these atoms, ions, or molecules that make up this crystal structure, what you get is a space lattice, right? Space is, we know that space is, we consider 3 dimensional, right? Space is 3 dimensions: x-axis, y-axis, and z-axis, right? So if you draw the location of these atoms, ions, or molecules, right, constituent particles of crystal in 3 dimensions, right, that is known as crystal lattice or space lattice, right? Crystal lattice, lattice is structure, so it represents the structure of the crystal, right? Now if we talk about 2 dimensions, right, 2 dimensions is like this is your plane of paper, right? Suppose I have a wall, like wall is a 2 dimensions, is in 2 dimensions, right? We know that this is how bricks are arranged in walls, right? This is how bricks are arranged, right? Now if I join these points will tell me the geometry of these points, right, or the symmetry. It will tell me the lines that I join. This will tell me how these points are arranged, right? How these points are arranged. If I keep joining these points, that represents the bricks that make up the complete wall. If I join all these points, what I get, if I keep joining these these points, what I get is a complete wall, the structure of complete wall, right? So this structure of complete wall, similarly here would be, we have the walls like all these points. Similarly, so the wall that we get on joining all these points, the points represents the bricks, right? If I keep joining all these points, what I get is the complete wall. This complete wall is this complete structure. When you join these points, this complete structure this shows you the structure of wall. This is how wall looks like. So this wall is like your crystal lattice, right? Now there is one more important thing to this. If you see here in this crystal structure, there is a similar pattern, right? This is a similar pattern, right? This is a similar pattern which is repeating again and again, right? This is a pattern. This is the basic pattern which you will see that it's repeated, right, throughout the length of the crystal in all 3 dimensions, right? So this shows the basic structure, right? How constituent particles, which are atoms, ions, or molecules, are arranged within the crystal, right? This smallest structure, right, shows you how atoms, ions or molecules are arranged within crystal, right? Similarly, if we talk about this wall is made of a repeating structure. If I try to draw that structure, it's something like this, right? If I draw these points, right, 4 points, and I join them, right, this is how, this is the basic, this is kind of a basic unit of this complete wall, and this represents a wall, I'm sorry, a brick, right? One brick in this complete structure of wall, right, will represent this structure. This is one brick, and if you keep repeating this structure, you will get this entire wall, right? Because how a wall is built, when you keep adding these bricks, right, so one brick represents that basic structure of that entire wall, right? So this is your brick, right? This represents how other bricks are arranged in this complete wall, right? If you keep repeating this in different directions, right, like this, you will get the complete wall, right, this structure. So this basic structure, right, that tells you, or that gives you the basic idea of how these atoms, ions or molecules are arranged, right, in the crystal, in the structure of crystal, how these atoms, ions or molecules are located, right, in the crystal, or how they are arranged in the crystal, right? This basic unit is known as your unit cell. Here, if you find the basically how these atoms, ions or molecules are arranged, you will get this kind of structure, right? So this is known as your unit cell, right? In a way, this unit cell gives the entire picture of the crystal, right? If you keep repeating this unit cell, what you get is the complete structure of the crystal, right? If you repeat this unit cell in all the 3 dimensions, since crystals are 3 dimensional, right? If you keep repeating this basic structure in all the 3 dimensions, what you get is the complete structure of the crystal, right? So this basic unit is known as your unit cell, right? This is important. So this is your space lattice, right, that tells you how atoms, ions or molecules are arranged in the crystal, right? It tells you the structure of crystal, and the unit cell is the smallest part of this crystal structure or of this space lattice, right? So unit cell is smallest part of space lattice or crystal lattice, right? And when you keep repeating this smallest unit, right, or this smallest part, it will generate the entire crystal, right? Smallest part of space lattice, which on repeating in different directions, that means which on repeating in 3 dimensions in different directions, generates the entire crystal, generates the entire crystal structure, right? So this is your unit cell, right? Now if we talk about in 2 dimensions, just to understand it, if this is 2 dimension, we can take 4 points in 2 dimensions, right? Because 2 dimensions will run like this and this, similarly this way and this way, right? In how many ways these 4 points can be arranged in 2 dimensions, right? There are, one is your square form, rectangle, parallelogram, and your rhombus, right? These are the 4 ways in which these 4 points can be arranged in 2 dimensions, right? So these different arrangement of these points give you different lattices, right? So when 4 points are joined to form a square, we get a square lattice. Similarly, if 4 points are joined to form a rectangle, so what you get is a rectangular lattice, right? Similarly, you have a parallelogram, rhombic lattice, and hexagonal lattice, right? Now, such a regular arrangement of constituent particles, right, the above, of a crystal in 3-dimensional space is your crystal lattice. This is important. What is a crystal lattice and what is a unit cell? It's, in simple terms, crystal lattice will tell you how constituent particles in a 3-dimensional crystal is arranged in x-axis, y-axis, and z-axis, right? And once you get the entire crystal lattice, right, then if you notice, right, there is, if similar to this, if you notice, there is a small portion of that crystal lattice which is kind of repeated again and again, right? That smallest portion of the crystal lattice, right, is known as unit cell, right? Similar to this, we have described wall, right? The entire wall is your crystal lattice, right? And one brick, which when repeated again and again, is your unit cell. So unit cell can generate the entire lattice, crystal lattice, if it is repeated again and again in different directions, right? So this is your concept of crystal lattice and unit cell, right? Now, since we said these are different types of crystal lattices in 2 dimensions, like I said, square, rectangle, rhombus, right? So there is square lattice, right, rectangular lattice. If you join these 4 points, right, it may form a rectangle, it may form a square, right, it may form a rhombus like this, right? So depending on how these points are joined, you have square lattice, rectangular lattice, right, parallelogram lattice, right, rhombic lattice, hexagonal lattice, right? This is in 2 dimensions. And unit cell would be square unit cell, right, rectangle unit cell, right? These are the kind of unit cells that you get. You can see these things in your books, right? So now you have some characteristics of these unit cells, right? These unit cells, it's been observed that in most of the unit cells, these points, right, these points are present only at the corners, right? This kind of unit cell is your primitive or basic unit cell, right? Now if in addition to corners, these points, lattice points, right, or these, and the lattice, these points represents nothing but the location of these constituent particles, right? And if it is present in the center also, right, or if these points are present at other locations in addition to the 4 corners, then what we get is a centered unit cell, right? If these lattice points lattice points are present at other positions, at other positions in addition to the four corners. We call it a centered unit cell. Centered unit cell, right? So this is your basic unit cell, primitive unit cell, or centered unit cell, right? Now there are some important characteristics of these crystal lattices, right? What do we call to these points? The points that I represented, right, is known as, these points are known as lattice points, right? And each point, we know, we have already discussed that each point in the crystal lattice, right, represents the location of the atom, ion, or a molecule in the structure of crystal, right? And the points are joined by lines just to represent the geometry of crystals, right? Just to represent the geometry of lattice. So this is your, if say if I try to join, if I try to make the lattice of this structure, it would be somewhat like this. Right? This is how it would be built. Right? So all these points, right, it would be like this. All these points, this is what I'm drawing is a crystal lattice looking at the location of, or the position of, constituent particles in the structure of crystal, right? These, when I get complete with this, right, what I get is a crystal lattice or a space lattice, right? And these points, right, that represents atoms, ions, or molecules, these points are known as lattice points, right? And these lattice points represents atoms, ions, or molecules in the structure of crystal, right? Represents the constituent particles or atoms, ions, or molecules in the structure of crystals. Lattice points represent constituent particle, right, in the structure of crystal. Now if I join these lines, right, look, I'm joining this point and it will generate the same crystal. Joining, I have to join all the points, right? This is what it will look like. Then it will keep continuing, right? So you will see that this kind of structure is getting repeated, right? This structure is your, using this smallest structure you can build this entire crystal lattice. This smallest structure is your unit cell, right? Since using this you can build the entire crystal, this is your building block. We call it a building block of crystal, right? Now just to take an example, if we take a cube, if I take a cubic crystal and if I break the cubic crystal, right, and if I break that cubic crystal, keep continuing breaking it, I'll reach at a point when I get the smallest crystal, right? The smallest crystal, that would also be a cubic crystal, right? So that smallest crystal, right, which I get on repeated breaking is your unit cell, right? And that the big crystal is your, represents your entire crystal, which is your crystal lattice, right? So you can get the crystal lattice if you keep repeating this unit cell in different directions in 3 dimensions, right? So if you look at this, if you look at the structure of this crystal in 3 dimensions, right? There are some parameters of this unit cell, right? There are some parameters of the unit cell. If you draw this unit cell, right, in 3 dimensions, it would look like this. This is your x-axis, this is your y-axis, this is your x-axis, and this is your z-axis. So this A, B and C, these are your, if I represent the smallest unit cell in 3 dimensions, in x-axis, y-axis and z-axis, right, this is what I get, right? We have 3 points, 3 edges, right? These are the parameters of unit cell, right? So its dimensions along the 3 edges A, B and C, right? These A, B and C represents the dimensions of unit cell. There are 2 things. Unit cell parameters. What we are basically discussing is unit cell parameters. And these unit cell parameters decides the shape and size of the unit cell. And there are 2 parameters, right? This unit cell parameters, I'll just write it over here, decides the shape and size of the unit cell. These are length of these 3 edges and the angle between these, right? So there are 2 unit cell parameters. First is the dimensions along the 3 axes, all around the 3 edges A, B and C, right? These edges may or may not be mutually perpendicular, right? So these edges may or may not be perpendicular, right? And the angle between these edges, right? The angle between these edges, alpha between the edges B and C, right? B and C, there is an alpha angle between B and C, we say, right? Then beta between A and C, right? Beta angle is between A and C, and this is gamma angle between B and A, right? So these 2 parameters, the length of these edges, right, A, B and C, right, and the angle between these edges, right, decides the shape and size of the unit cell, right? And depending on the shape, depending on these edges and these angle between the edges, we have 7 types of crystal, which is known as 7 crystal systems, right, which we will discuss more in the next video lecture. And we have Bravais lattices also, that we will be discussing again in the next video lecture, right? So let's just quickly talk about these kind of unit cells. Unit cells, we said, in unit cells the lattice points may be present at the corners, right, or they may be present at other positions, right? If say we have a unit cell, cubic unit cell, right, if the point instead of corners is present at the center, we call it the body centered cubic cell. This is your BCC, body centered unit cell, right? If on the other hand these lattice points are present, say this point is present at the 4 corners, if it is present at the opposite faces here, this is known as edge centered unit cell, right? And if it is present at each face of the crystal, this is known as face centered unit cell, right? So depending on the location of these lattice point, if it is present at each face, it is face centered. If it is present only at the center and at the corners, it is body centered. And if it is present at the opposite corners, right,